Good day, sir. My name is Kyle Kane Benito from BSMT1-9. This is my project in navigation. So we will start to the first topic, the Earth's coordinate system, the latitude and longitude. The first step in converting the information contained in the real world onto the piece of paper was to devise a system where everything could be uniquely located in the world. Every early maps which usually show small local and regional areas used of grid techniques which relied on simply measuring the distance and direction between points and interest and plotting this onto the piece of paper. This method assumed that the earth was flat, with the general agreement that the earth was, in fact, around a different methodology needed to be developed. The system that has been developed over many centuries is called latitude and longitude. The location and measurements of latitude and longitude essentially involves complex mathematics, especially geometry, and a series of international agreements, conventions for recording location on the surface of the earth. The latitude. The first convention to develop was latitude. This is based on long-term astronomical observation about how the sun is perceived to move across the surface of the earth. This observation also developed the convention that the sun rises in the east and sets in the west, in the south during European winter, and in the north in European summer. It was agreed that a line round the center of the earth would be called the equator. This would be numbered as 0 degrees of latitude. From the equator, a series of parallel lines were recognized with the most northern and southern point being called the North Pole and the South Pole. This would be numbered as 90 degrees north and south respectively, 90 degrees north and 90 degrees south. Four significance lines of latitude were also agreed upon. These are 0 degree equator, 23.5 degree north and south, the tropics called Cancer in the north and Capricorn in the south. Between these two, at some times of the year, the sun is directly overhead. Beyond each of these, the sun is never directly overhead. 66 degrees north and south, the polar circles, 90 degrees north and south, the poles. Beyond the poles and the polar circle, 24 hours of daily light. Midnight sun is possibly summer, and 24 hours without any daylight is possibly in winter. Because lines of latitude are like slices through the earth, they have different lengths. For example, the equator is 40,075 kilometers long. The Antarctic Circle is 7,662 kilometers long. The South Pole is 0 kilometers long. For obvious reasons, lines of latitude are called parallels. Longitude. Defining longitude was much more difficult as could not be based on observation of movements of the sun. It was a part influenced by the discovery of magnetic north, but on ultimately longitude is most based on abstract mathematical, geometric concepts. The convention eventually agreed upon was a series of radiating lines which run vertically around the earth. They connected at both ends at the North Pole and the South Pole. As a result of this, a series of slices much like a slices of an orange are created. These are pointed at their end and broadest in the middle. It was agreed that a primary line of longitude should be identified at that this should be 0 degrees of longitude. For a considerable period of time, the issue of which line of longitude was to be the primary line could be not agreed. For obvious religion reasons, early European maps often used Jerusalem as the primary line of longitude because it is status a century of learning around early maps maker, such as Ptolemy was used Alexandria in Egypt. More commonly true, for periodic reason, many countries choose one of their cities. A few European examples are Copenhagen, Madrid, Paris, and St. Petersburg. while in the United States of America, Washington and Philadelphia has been chosen. Eventually, in October 1884, at the International Meridian Conference, it was agreed that the line of longitude that runs through the Royal Observatory, Greenwich in United Kingdom, was to be adopted as the standard primary line of longitude. Radiating to the east and to the west would be 180 degree of longitude. This would meet at the opposite side of the Earth and form a joint 180-degree line of longitude, with 180-degree east and 180-degree west being the same line. Line of longitude are called meridians. Add to add to two together, combine latitude and longitude together, and we have a system to record the location for any features on the surface of the Earth uniquely. So the second topic is the map projection. In category, a map projection is a way of flattening a globe surface into a plane in order to make a map. This requires a systematic transformation of the longitude and the latitude of locations for the surface of the globe into location on a plane. Flattening the Earth. It is impossible to flattening the Earth without distorting in some fashion. Consider an orange peel. If you want to try and lay it flat, you can have it to stretch it, squash it, and tear it. Likewise, with the Earth, if we want to make a map, we need to distort the Earth's surface of flatten it. The good news is the map projection allows us to distort systematically. We know exactly how things are being stretched or squashed at any given point. We have many different map projection because each has different pattern and distortion. There is more than one way to flatten an orange peel. Some projection can even perceive contains features of the Earth without distorting them. True, they can perceive everything. Projection properties. So we often talk about map projection in terms of the way in which they distorted or perceive certain things about the Earth, which are we call projection properties. These are the four main properties. So the area, this is the area, and so notice the Greenland is about as big as South America on a Mercator projection. In really in reality, South America is 8 times larger than Greenland. The Mercator projection doesn't perceive area correctly, especially as you can get closer to the poles. On the other hand, one kind of projection that doesn't distort area is the cylindrical equal area. So, notice here how Greenland looks right size and compare South America. Projection with perceived area are called equivalent and to equal area projections. Map projections either perceive area everywhere or distorted it everywhere. This an all or nothing property. So choosing a projection, since there are so many projections, the question becomes which one should you use? As you may imagine, the fact that there are many means there is no best projection. Each has advantages and disadvantages, and it's better suited to certain situation. Here are some questions to ask yourself when choosing a projection. This there are any specific property that you need to perceive. Remember that some projection will keep areas, forms, distance, and direction free of distortion. Sometimes the subject of mapping is better perceived by perceiving one of these properties. Here are some examples. Area. Maps is density demand equal area projections. If you're working with a data set of person per square mile, for example, your map needs to make sure each square mile look at the same size. If areas get deserted, some place will start looking sparser or denser than they really are. Second is form. So, conformal projection are often good for general purpose reference mapping. where we want to keep places looking recognized and familiar. They are also often used for navigation charts by perceiving local angles. They don't desert paths. A 45-degree turnout the turnout the Earth looks like an 45-degree turns on the map, whereas the angles were distorted. This would be the case, not be the case. Distance. If you'd like to show visually how far one thing is from another, you're going to need a perceived distance. Sometimes airport use this to show the cities they fly to. Directions. Also helpful for navigation. Sometimes it's useful to loxodrome as straight lines. The Mercator, for example, was invented in Renaissance sailors to make it easier for them to plot courses. They could draw a straight line on the map, and this would tell them exactly which compass heading to use the head home. On the other hand, if you're plotting an airplane, you might want to show great circles as straight lines so that you can get from A to B while using the least fuel. So there are the plenty of reasons to preserve each this of these properties. The above are simply examples to get you thinking. Some there some other consideration. So how big an area are you mapping? If you're mapping the world and don't need it to preserve a specific property, a compromise projection is your best bet. Number two, does the area of your map tend to run north, south, or east, west? Different projection have difficult distortion patterns. Some some like the alberqual area conic dist- distort more as you go north or south, but don't distort much you east or west. So they're good for mapping an area like United States. They're not good for mapping in a country like Chile, through which runs north-south, and transverse Mercator, different from plain Mercator, desert a lot east-west, but doesn't desert very much north-south, so it would be a better choice for Chile. What will your readers think about it? For example, while many readers may be familiar with the Mercator, the less familiar distortion they see is azimuthal equidistant may throw them off, or perhaps intergi them and cause them to pay more attention to your map. Likewise, people are used to seeing the US map with something like an Albert equal area conic, which give it its curved appearance. Seeing the US in cylindrical equal area might not look right to some readers, despite there being nothing wrong with other projection. So this is the picture, and so the general information and nautical chart, DLAT and DLONG. So this is our third topic. So in nautical chart is a graphic presentation of a sea area and adjacent coastal regions. Depending on the scale of the chart, it may show depths of water and heights of land. Through topographic map, natural features of the seabed, details of the coastline, navigational hazard, location of the natural and human-made aids to navigation, information on tides and currents, local details of the Earth magnetic field, and human-made structures such as harbor, buildings, and bridges. Nautical charts are essentially tools for marine navigation. Many countries require vessels, especially commerce ships, and carry them. Nautical charting may take the form of charts printed on paper or computerized electronic navigational charts. Recent technologies have made able paper charts, which are printed on demand with cartographic data that has been downloaded on the commercial printing company as recently as the night before printing. With each daily download, critical data such as a local notice of marines are added on the demand charts files so that these charts are up to date the time of printing. So these are the symbols and the abbreviation of the nautical charts. So A is chart number, title, and marginal notes. So here is the abbreviation. And B, position, distance, direction, and compass. C, natural features. D, cultural features. E, the landmarks. F, ports. H, tides and currents. I, depths. J, nature of the seabed. K, rocks, wrecks, and obstructions. L, offshore installations. M, trucks and routes. N, areas and limits. P, lights. Q, buoys and beacons. R, fog signals. S, radar, radio and satellite navigation system. T, service. U, small crafts, leisure facilities. And that's all. Thank you for listening.